Alright, welcome back. MECH2320 motor control. We're on chapter 37 talking about motor installation. Alright, now remember, a lot of this might happen. There's a lot of companies out there that actually, design and develop and create the whole building and everything that goes in it. So a lot of that might happen by them. But, when you're installing new equipment or you have a whole line change or those sort of things, that's when it might fall on you, at the workplace. So there's a lot of companies that design a lot of things, but you're going to have to be the one that puts it together. Or you might need to, replace an existing motor or do different things like that. So that's where this is going to come in handy. But by the end of this, all right, I don't expect you to know the National Electric Code. Okay, it's a very thick book, but you have to use it for rating all kinds of things: the right wire size, the right starter size, the right horsepower motor to do the job, how to overload size things. So it's really kind of getting familiar with when you get to do an install or things like that. It's very imperative that you use the NEC, the National Electric Code, because that's what everything is designed by and what you have to follow. And those all tie in with NEMA and UL and all those other companies that give all the requirements necessary to operate, within codes and to operate things reasonably and in a safe manner. So it's very important for that piece. Okay, so if we talk about the motor nameplate data, we've kind of gone over this in other classes before. In the mechanical class, you looked at a motor nameplate, and it tells you all the specifics from the manufacturer. It tells you how to connect it. So if it's a motor that operates on two voltages here, so this one's a 208 or 230/460, you can see if you want the low voltage, the 208 voltage, you would use the line connections on the left. If you wanted the high voltage, you would use the line connections on the right. Okay, that should always usually tell you the manufacturer's name. So you should be able to have access to all the documentation on that motor. It's going to tell you the horsepower. Alright, so in this case, if we're looking at this nameplate, we have a 1 horsepower motor. It's going to tell us that it's operating at 60 hertz, so that tells me I'm going to probably use this motor in America. Alright, and it tells you the number of 3 phases, so it's a 3-phase motor. It tells you the revolutions per minute, so it's 1720. Okay, and it's constant, and it's just going to tell you all those different important things that you need to look at. Okay, so it'll tell you the enclosure type that it needs to go in. I remember we talked about that, in the manufacture or in the mechanical class. Making sure, it depends, right? We're in textiles. We got to be more, explosion proof or things like that, so that we don't, arc some lint or things like that. Or if we're outside non-stop, we got to be protected from the elements, things like that. So, very important. So that's kind of what like the NEMA Design B is, the INSB, those type of different things. That way what temperature, that it's going to be at and how hot it can get in those different types of things, the frame. Alright, and then it tells you what type of motor it is. In this case, if we're looking at this motor nameplate, we're looking, and it's called an induction motor. Okay, we know what all those are. But, just all the different things that we can take a look at and understand, the duty cycle, okay, the safety factor, all those, the model number, the serial number, so that you can look those up if you need, connection diagrams and things like that, because they might have gotten, scratched off. Now, it's supposed to be on a nice plate here that's protected, so those sort of things can't happen, but, you never know. It might work out and you only get parts of it, so you need to be able to look everything else up online or go back and look at a catalog where you ordered. Okay, so the different things that we need to use: current, wire size, motor starter, all those different things. NEC code book, so very thick. When I was working in industry, I had to know parts of this in and out, because I was sizing motor starters and making sure that I had the right size wire running, and all those different things. And there's a difference if we're running control cables versus power cables and those sort of things. How much you can put in conduit, how much of a cable tray you can fill, all those different things. So we use the NEC, for those things. DC and AC current, 2-phase, 3-phase motors, all those different things. So we can use this is literally like right out of the NEC code book. So it's going to tell you, the average amperage rating here, So if we're running a quarter horsepower motor at 90 volts, okay, we have to know that we're going to pull about 4 amps. That's important because we have to size the wire correctly so that we don't melt the wire. And then we have to know the right wire size. So you can read through this table, look at the horsepower and then what, voltage we're running it at, how much current's actually going to go through there. And we really have to make sure, and it's very important, all right, what the full load current is and sizing the wire correctly, okay? So this is just looking at, single phase, okay, what's going on. So now if we look, a third horsepower at 115 volts is going to give us about 7.2 amps. Okay, same motor, 230 volts, all right, is going to give us 3.6 amps. So just different looking at this. All right, so let's take a look at an example here. So we have a 3/4 horsepower single phase squirrel cage motor. We got it connected to 240. What's the full load current for this? Okay, 6.9 amps. So it's really just being able to read this table. 3/4 horsepower. We're operating 240 volt, which is the same as 230 for us, okay? And it's at 6.9 amps. So that's the full load current, and that's what we're going to have to size everything around so that we don't fry wires and do that sort of thing. Okay, so it gets very important. Okay, so this is full load 3-phase. So this is right out of the NEC codebook, full load 3-phase. You can take a look at it, and really it's just a matter of lining up the row and column based on what you have. Okay, so it's very, very important. So I keep talking about wire size. It's technically called conductor size, all right, for a motor, but it's the wire size, because you don't have the right wire and you draw too much current, it melts, okay, and snaps and blows. So very, very, very important. Also, it needs to make sure it has a temperature rating. And remember that temperature rating is not ambient temperature outside. It's because we know that this much current produces this much heat, and you don't want to melt the wire. Okay, so very important. So this is a page right out of that book, okay? You might have seen this page before in the electrical class when we started talking about impedance on a line or resistance on a line, and you had 1,000 feet of this gauge cable, how much total resistance would be in the line. And that's important, and those are factors that you got to take into account here. Okay, but on the left-hand side, we have our AWG, okay, our wire size, okay, or it's in K circular mils. So remember, 18 gauge wire is very small. We're using, just so you have an idea, control wiring, that's going to be in the 20s, 22, 24, 26. It's very small, thin control wiring. So what you're running in your house is probably conductor 14. Okay, you got like a 2-conductor 14 with a ground. So just so you have an idea, that cable, that goes to all the outlets in your house, that's a 14. If you have some good power cords, though, you're probably using a 12. Okay, but it just kind of tells you you gotta go with all the different things, and all those little TW, UF, all those different things. Those are different ratings, and shielding that's on that stuff as well. So and what it's rated for. So that's how they control, like the temperature used. So be very careful when you choose these, because remember, aluminum conducts heat way better than copper. So if I were you, I would never use aluminum for anything for wiring. It can start fires, it can overheat, just lots of issues with aluminum. I generally base everything off of copper wiring. Okay, so then you just got to be able, we're going to go through kind of how to use the chart here, based on the size. Alright, so we have a 7.5 horsepower single phase squirrel cage motor. It's connected to a 120 volt AC line. Okay, it says the nameplate current is 76 amps. Okay, the conductors are copper with type TW insulation. We want to calculate the conductor size. So we're going to size the wire based on these specifications here. Okay, so one, we got to find the full load current. So we got 7.5 horsepower at 120 volts. So we can see down here, even though the nameplate current on the motor is 76 amps, when we hook this up, okay, the full load max current that this thing's probably going to draw is 80 amps. So you have to size it to 80 amps. Okay, then we oversize it just in case. So a rule of thumb is 25%. So we're going to take 80 times 1.25 for oversizing. Okay, so we're going to size this for 100 amps. Okay, that way nothing gets blown and everything's is protected, and we can handle the full load voltage, and we're not at the threshold of the full load voltage. We don't want to size it to 80 amps because if it draws 80 amps, we're right on the brink of something bad happening. So we want to make sure that we allow, more to happen. Always oversizing, okay? So based on, the calculations that we just had, we're coming to the wire chart now. So remember, we're looking for, even though this motor's, nameplate current is 76 amps, its full load current is 80 amps. Okay, we want to oversize that, so we multiply that by 1.25. So we get 100 amps that we're looking for when we do this. Okay, so we've got to go down and we've got to find, the amount of current that we have and then base it on the wire size. So if we look right here, okay, there's not a nice specific 100 amps. Okay, there's 110 and 95. Well, we want to be at 100, so we're going to step up. Okay, so we're going to use the 110 for our current. Okay, so we're going to say the current's going to be 110 and we want to do it. And we're looking for type TW insulation. So we have to use this column right here. So we're going to use 100 amps, which is really 100, it's going to be rated for 110 amps now. Alright, so we're going to use a wire size of 1. So there's how we size wire. Alright, so I did a lot of this in industry. Just making sure you go through, do the right calculation, get the right wire size, make sure nothing blows up. Alright, so we choose a number 1 gauge conductor. Okay, now it's a single 120 volt single phase, but you still need your hot, neutral, and ground, so you make sure that they are all the same size. The hot, neutral, and ground all are going to be a number 1. So technically, right, you're going to have a 2 conductor with a ground, or you could just run a 3 conductor and know that one of those is going to go to ground. Okay. So there's how you size wire. Alright, so we got oversized load. Okay, so we just talked about the nameplate current. That's the rating of the motor used. Okay, but we got to make sure that we take into account all the other aspects of it. Other things we got to look at is its service factor and its temperature. Okay, so if we want to determine what a locked rotor current is, okay, we're going to take a look at this chart. So we can go down and we look at the code letters. Okay, A to V, those indicate the rotor bars. Okay, the rotor bars. Okay, that determines the maximum amount of starting current. So remember when we did all the things about starting the motors, and we talked about, what the inrush current is at the beginning. All right, that's what we're talking about here, the startup current. So to calculate that, we're going to multiply by a kVA, kilovolt amp hours. All right. Rating by horsepower rated and divided by applied voltage. So we're going to do that. So that's what it's going to be. So we got to overcome the rotor lock. Okay. So that's what we would use that for. Okay. If we want to do short circuit protection, it's going to tell us here, okay, what size of fuse or racks rating that we're going to put on this on our ground fault protection device. Okay. So how are we going to protect it? So it's going to tell you the type of motor. Okay, and the type of fuse that we could potentially use, and then the breaker size. Okay, so it just kind of depends, on what the type of motor you have. And we've talked about all these, right? Single phase motors, squirrel cage motors, synchronous, wound, okay, DC motors. We've talked about all these, so it just kind of applies. Then we need the starter size based on that, right? So the starter size, that's going to be rated by the motor type, the horsepower, and the connected voltage that we're going to be running this. Okay. Where you can look at the NEMA and IEC, you also pull this directly out of the National Electric Code. Okay, so the starter size will come from that as well. So it's more like, taking a look at this chart here, on the what we got on the left here, right? We have NEMA size 0, 0, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Tells you what the continuous amp, current rating is going to be, and it depends on which, what the horsepower is going to be for that based on the voltage. Okay, so if we have like a 2 horsepower motor running off a 460 volt AC, it's going to have a constant current of 9 amps, so we're going to use a NEMA size 0, 0 to do that. Okay, so that's using the NEMA. If we look at the IEC, that's the chart that's in color on the right. So you have your starter size A through Z, and that's going to be based on the amps that's going through, the motor voltage, and the horsepower that we can draw from that. So we'll do an example here. All right, we're going to stick with that same example so we can kind of see what the starter size would be if we were taking the same motor and doing everything all the way through. Okay, so first, that example that we've been doing is 7.5 horsepower single phase squirrel cage motor. I'm connecting it to a 120 volt AC line. It says, remember, the nameplate was 76 amps, the max full load current was 80 amps. Alright, we designed the conductor to be 100 amps, right? Or it's actually being 110 amps, and we chose a number 1. Okay, so in this case though, we go down and we find on the chart the max operating amps. Okay, there isn't one for 80, but there is one for 85, and that's the one we're going to choose. You always round up, don't round down to 73. Okay, just because we're at 76, round up. Okay, we're basing it on our full load current. Okay, and that's what we got off of one of the previous tables and calculations. So we're looking at this, right? We have to look at our horsepower, 7.5 horsepower. That matches. Our current will be, 80 amps, so we have to go with 85 here. And then the voltage we're using is 120 volts, so that's still the 110. So our IEC starter size, we would buy a size L starter when we do this. Okay? If it was NEMA, it would be a size 3 NEMA starter. Okay, so it just depends on which starter you're going with when you do this design. Are you using NEMA or IEC? They're equivalent, but notice the NEMA has goes up to 90 amps, okay, for this same motor, and what the horsepower goes up to for that. Under, let's say we were doing 120, so it goes up to 30 horsepower. So we would have a NEMA size 3 starter. So we're basing everything, guys, on current, not on voltage or things. Voltage makes its way in there, but current is the most important thing, because that's what's drawing the heat, and that's what's going to cause the biggest issues. Okay, so just make sure if you're in the workplace or you ever have to do this, that you're sizing things to NEMA or IEC. So for the most part, it just kind of depends on what country you're in and things like that, what you're going to work with, or what the operating equipment is, that you have in the plant. So just make sure that you know, though, that a NEMA 3 size or NEMA size 3 starter is pretty equivalent to an IEC starter size L. So it's just how they rate in everything and how you design it based on NEMA or IEC specs. Okay, so you'll be able to look on the starter size, and it'll tell you if it's NEMA size 3 or IEC. You'll look through your vendor catalog. So if you got an order from Allen Bradley or Siemens or things like that, you'll see it'll say on there that it's a NEMA size 3 or it's an IEC size L type of starter and things like that. But guys, I mean, this is truly how it works. This is the meat and potatoes when you have to replace equipment or size everything properly. If you're starting from ground zero or scratch, or you're working for a company like I did that actually installs and builds these type of manufacturing facilities. So not only does it work in the manufacturing maintenance type thing, but there are companies that design and build the plants for these companies, right? So I mean, we have Nissan locally here, but there was a company, it wasn't Nissan. Nissan probably doesn't design and build their own buildings. They give the spec and they have another company go in it, because Nissan's skill is designing and making cars, not designing and making buildings. Does that make sense? Same with the Bridgestone plant that's local, right? Bridgestone probably did not design the plant. They hired a construction and engineering company that designed all that and built all that, because Bridgestone's in the business of making tires and making tires better and doing those sort of things, not in the business of building their own manufacturing buildings. So that's where that all kind of comes into play. So I was on the other end of that, where I was in industry working on building production buildings and things like that. So I worked on natural gas plants, power plants, those sort of things when we did all this. But enough about me, guys. Hopefully you guys learned something about how we size everything in here. Else, guys, have a great day. I will see you in class.